Hi everyone, welcome back to our basic math or economics. Now, in our last video, we talked about what exactly a derivative is, and this one I actually want to move forward and actually start calculating some derivatives. So actually, let's just jump right in. Let's start talking about them. So this video, we're going to talk about what we call commonly used derivatives. And realistically, we see three of our most common types of derivatives used in economics. The first one we classify as the power rule. And honestly, that's going to be the vast majority of derivatives that you're going to do in economics, and it is an application of this rule, and it is a very straightforward, very simple rule. The second one we like to see is called natural logarithms, and we like to see this functional form used for utility functions. It's nice that it's increasing, it's concave, and truth be told, it has a very easy derivative. So we like to use that one a lot. And lastly, we have the exponential function. And we'll see that one sometimes in demand function. It gives them some neat properties for the price elasticity of demand. Now, each of these have their own techniques for calculating their derivatives, so I want to go over them. Now, if you've taken calculus and you remember it well from the past, you might remember that there are other rules for things like trigonometric ratios, for other things that are, honestly are quite complicated. The good news is we really don't use them in economics, so, we don't really need to review them that much. We're going to stick to these three main topics. So the first one is our power rule. And the power rule can be used on almost any polynomial to calculate its derivative. And all a polynomial is just a series of exponents of a variable, and usually they're added together. So for example, we have a polynomial right here, x to the fourth power plus 2x plus 4. Each of those individual terms are a polynomial, and we can chain polynomials together. And that's what we're going to use the power rule on. So anyways, I want to show you the power rule through an example. So let's take a look at our total cost function right here. And this is an example of an actual total cost function that you could see when studying economics. So we have 10 plus 3q plus 4q squared plus q cubed. That's hard to say, actually. Anyways, what we want to do is I want to take this total cost function and I want to calculate a marginal cost function from it. And remember that whenever you hear the word marginal, you should be thinking of converting something from a total to, using its derivative to convert it to a marginal. Total to marginal via the derivative. So that's a quick hint right there of whenever you hear a marginal, what you should do. You should take a derivative. So anyways, in order to calculate the derivative of any kind of a function using a power rule, we're going to follow the two main steps. The first step, if the term does not contain the variable we're differentiating with respect to, so we're differentiating with respect to q in this problem because q is our quantity, it's our variable of interest. So if it doesn't have a q at all, we leave it alone. One of the main rules in calculus is that the derivative of a constant is 0, so we just delete it. Second, if the term contains the variable we're differentiating with respect to, we multiply that variable's coefficient by its exponent, then decrease that variable's exponent by 1. And that's going to be consistent all the time for the power rule. Multiply the coefficient by the exponent, then decrease it by 1. That's all there is to it, really. So let's walk through it. We're going to look at each of our four terms individually. So our first term in that expression is 10, and it does not contain our variable q. So that's a constant, and the derivative of a constant is simply 0, which means that we can just delete it from our derivative. It's not going to show up at all, because if we're adding anything to 0, we might as well not even write it. So our second term, 3q. So since it has the variable q in it, we're going to apply the power rule to this situation. So first, we're going to multiply the coefficient of the variable, which is 3 in this case, that's just the number that's out in the front, by the variable's exponent, which is 1, because q is just q to the first power. I mean, we just don't write that. So the new coefficient for our marginal cost, or our derivative in this case, is going to be 3 times 1, or just simply 3. Next, we're going to reduce the exponent for q by 1. So this was q to the first power, and we're going to subtract 1 for that. That gives us q to the 0th power. And anything raised to the 0th power is equal to 1. So q to the 0th power is equal to 1. And what that means is that the first term in our marginal cost function is simply going to be 3. So we combine our two results together, and we get our individual terms. Now let's move on to our second term, 4q squared. Again, it's got a q in it, so we can apply the power rule. First, we're going to take the term's coefficient, 4, we're going to multiply it by its exponent, 2, and we're going to obtain the coefficient for this term in our derivative, which is going to be 4 times 2, or 8. Next, we're going to decrease the exponent of the variable by 1. So it's going to be q to the 2 minus 1 power, which is just q to the 1, which I can just delete the 1 at that point and just say it's going to be equal to q. So I'm going to put them together, and I get my second term of my marginal cost function, 8q. So I take the first part and the second part and just put it right together. One more term to go, and this is going to be q cubed. So again, it contains the variable q, so I'm going to apply the power rule. So first, I'm going to take the coefficient, which is just 1 in this case. I don't have it written there because it's 1, but it's still there. I'm going to multiply it by its exponent, which is 3, and I'm going to get the coefficient of that term in our derivative, 3 times 1, which is just going to be equal to 3 in this case. Then I'm just going to decrease the exponent of the variable by 1, so q to the 3 minus 1 power, or q squared. Putting them together, I end up with the last term of my marginal cost function is just 3q squared. We put it all together, just attach them to each other. So now that I've done all 4 terms in this expression, I can now put it all together. And I can use that to assemble our marginal cost function, which is just going to be 3 plus 8q plus 3q squared. And that's it right there. That is my marginal cost function as from my total cost function. We just applied the first derivative and we got it without an issue. So what's neat about the power rule is that it is a very general technique. It'll work on almost any polynomial, and the ones that it doesn't work on are very special cases, and we really don't need to worry about them right now. So what's also fascinating, and you're going to see this a lot, is that the exponents don't even have to be integers. We can use decimals, we can use negative numbers, we can use negative decimals. And those are going to be very common in utility and production functions. As long as we're following the same steps, we're going to get the correct answer. We can even have exponents that go from being positive to negative. That's very common in utility and production functions. It'll still work with the power rule. Some functions, however, are a bit more complicated and they're not technically polynomials. So the nice thing is that we do have rules to simplify their analysis. So what's neat is these rules are going to build on the power rule, and we're going to discuss them in the next video or the next session. So anyways, let's do our next one, which is going to be the natural logarithm. And we're going to see that commonly used as a functional form for utility functions. Now, a bit of a note is that in economics, we really don't use any other bases except the natural logarithm. Remember that a logarithm can have many bases. A lot of people like to use base 10 for logarithm, but in economics, we primarily stick to the natural logarithm. So if you're in an economics class and someone writes log x, it's safe to assume that they're referring to the natural logarithm. And actually, I'm going to do that as well. I know there are a lot of people who will get mad at me that I'm not writing ln, which is the natural logarithm. I'm writing log. But just trust me on this. A lot of your professors are going to do that too. If they write log x, they're talking about a natural logarithm in economics. So anyways, if I have a derivative of the form log of some function of x, the derivative is simply going to be, or f prime in this case, the derivative of g of x, g prime of x, divided by g of x. Now this may look really complicated, but it's actually extremely straightforward. So let's take a look at another example right here. So anyways, let's take a look at this utility function. U of x equals the log of 2x. Now let's figure out how to do this one. Let's calculate its marginal utility with respect to x. And again, I said marginal, which means that we're going to calculate a derivative of this case with respect to our variable of interest, or x. So anyways, going back to my formula, in this case, g of x is just going to equal 2x. It's just the argument that's inside of the logarithm. And I can use the power rule to calculate g prime of x in that case. So anyways, since 2x is a function of x, I can apply the power rule as normal. So first I'm going to multiply by its coefficient 2 by its exponent 1 to obtain the coefficient of g prime of x, 2 times 1, which equals 2. Next, I'm just going to decrease the exponent of x by 1, giving me x to the 1 minus 1th power, which is x to the 0, and again, anything raised to the 0th power is just equal to 1. So putting it together, I find that g prime of x is going to be equal to 2 in this case. And lastly, going back to my definition of the derivative of a natural logarithm, I can get my derivative from this, plugging it all in. G prime of x divided by g of x. So 2 for g prime of x divided by 2x for g of x, and that gives me 1 over x as my derivative. And that's it. That's all I need to do. I can do any combination of functions inside the natural logarithm, and it will always be that way. So like I was saying, it's a really easy derivative, and it works out quite nicely. So let's take a look at one more type of function. This one's called the exponential function. So the exponential function is the dichotomy of the natural logarithm, and it is frequently used in demand functions. I wouldn't say frequently, but it does get used. It has very interesting properties for the price elasticity of demand. So anyways, if I have the demand function of so my demand function Q of P, where Q is quantity and P is price, is E, which is representation of the exponential function, to the negative P power. So the P being the price in this case. That's going to give us a demand function. It's going to be similar to the shape of one that we can derive experimentally. It's got a nice curve to it. It behaves very well, and we like the properties of this one. It's close to reality. So anyways, if we have any kind of functional form of e to the g of x, and I'm using g of x as a general function. This is a function of p in this case. We could just replace the x with a p, and it's not a big deal. But the derivative of that function in this case is just going to be g prime of x, so the derivative of whatever the exponent of the exponential function is, times the original function. And that's a really neat property. The original function doesn't go away in the derivative. And that's what makes the exponential function so interesting in the case of calculus, because we just can't get rid of it. But anyways, let's take a look at this through an example. So let's consider this demand function. Q of P is equal to e to the negative p squared power. Let's calculate a derivative. Actually, let's go beyond that. Let's calculate the price elasticity of demand for any given price p. Now, a little bit of a dusting off of this. If you remember your formula for the price elasticity of demand, that's going to be the derivative of our quantity with respect to price. So there's something that we're going to want to calculate, times our price divided by our quantity. And usually we substitute back in the demand function for the quantity in this case. So we need to have the derivative of our demand function times price divided by our original demand function. So to figure this out, I'm actually going to need to calculate the derivative of our exponential function raised to the negative p squared power. And to get that, we're going to need to use both our power rule and the derivative of the exponential function rule. So let's work through that. So going back to that definition, I need to figure out what my g of x is. And it's pretty clear to see that in this case, g of x is negative x squared. Now again, I've replaced the p with an x here just for simplicity. You can do it as, you can leave everything as p's, and this will work out just fine. But I can calculate g prime of x using the power rule. So anyways, as before, since our variable is a function of x, first I'm going to multiply its coefficient, negative 1 in this case, by its exponent, which is 2, and I obtain the coefficient of g prime of x, negative 1 times 2, or negative 2. Next, I'm just going to decrease the exponent by 1, which gives me x to the 2 minus 1th power, or x to the 1, or just x. I can delete the exponent at that point. Putting it together, that gives me g prime of x is equal to negative 2x. Now, I can go back and I can calculate the derivative of my function by plugging in all of that information. So f prime of e to the negative p squared power is going to be equal to g prime of x times e to the g of x power, or negative 2x times e to the negative x squared. That's it. Just plug in that derivative and the original function as well. And to make this easier, let's go back from using x's back to p's. So I just replaced every instance of x with a p. And I get my derivative of that function is negative 2p times e to the negative p squared power, which lets me go back now, put it back into my formula for price elasticity of demand. Substituting it all in, I get negative 2p e to the negative p squared power times p divided by e to the negative p squared power. And if you'll notice, all of the exponential functions are going to cancel out in this case, which is, again, a very neat property of the price elasticity of demand for an exponential function. And I'm left with a price elasticity of demand equal to negative 2p squared. So as the price increases, we're going to find that we have a 1-to-1 increase in the elasticity of the actually, sorry, a 2-to-1 increase of the elasticity or the price elasticity of demand. Anyways, that's all for this video. In the next one, we're going to go over some commonly used rules for calculating derivatives. So thank you for watching.